CFD analysis of single turn flat pulsating heat pipe. So the first task will be to prepare the geometry of single turn flat pulsating heat pipe with the help of ANSYS design modeler. Second will be to prepare the mesh and apply the boundary conditions. Third one, to observe the contours of liquid volume fraction. So this is the geometry of single turn flat pulsating heat pipe. So you can see there are two sections. One it is air and second one it is water. So this is the one which is filled with the fluid. You can see the volume, that is 487.81 mm cube. Here it is 362.15. So we'll just check it out, what is the filling ratio of this. So we'll just go with the calculator. So first of all it is 362.15. So that has to be added with water, that is 487.81 plus 487.81. So the whole is 849.96. So this is the total volume. Now what I will do is I will divide 487.81 divided by so it is somewhere around 57% filling ratio. So when we consider this as a 57% of filling ratio, how the analysis can be done, that we are going to see. So this will be the part of the condenser where the heat rejection will take place. This will be your part of a evaporator. So with this we'll go on to prepare the next part, that is related to your mesh. So write down this. Right now this geometry has been prepared earlier, so you can align the fluid flow fluent over here. So simply click on fluid flow fluent and drag this in front of your geometry. So here we'll approach to the next part, that is related to your mesh. So first approach will be to produce a default mesh, so that okay, so we are approaching to the mesh, default mesh we are going to produce. This default mesh can be further modified, means it can be further turn into a fine mesh also, but that we can do later on also. We'll just check out how the results are been getting, or we'll check it out the statistics, number of node points and element. So it shows somewhere around 55,366. So these are the number of node points and element we are having. You can change the element size here, or you can keep it as it is also, in order to check how the results you are getting. So both of the way it can be done. So either you can just reduce the size of mesh over here and then can proceed further. So I will just go on to use this default mesh and will proceed further for the analysis. So right now just specify whichever we are having as a evaporator. Say for example I have this bottommost portion, I say it's evaporator. If I say this as evaporator, how the heat transfer will take place, so that we can understand from it. So simply you can select the whatever the surface you are having. So I will just specify this as a heater over here, and you can specify the remaining portion as a condenser. So select that portion and select as a condenser. Okay, now you can see on the left hand side there are two things. One, it is heater, which is at the bottom, and you can see it's a condenser. So normally the condenser area is quite bigger than your evaporator, so that the fluid will be subjected to the heat, the evaporation and condensation. So that's why this has been purposefully noted. Now you can make it update. So you can make this update, and you can see on the right hand side it is here, it is in front of mesh, it's a right click. So earlier it was not showing, now it is showing. Right click in front of your mesh. So in this situation, if you close the mesh window, that is also okay. So let's close the mesh window. Now check it in front of WB window, that is workbench window. You can see now you can edit here. So you can select a number of we can say processors also. I will just select 4 over here depending on my configuration of computer. Let's start the process. We'll go on to apply the boundary conditions over here. Now how many processes that you can use, it is available on. Okay, now you just check it out how many processes that can be used at a single time. So here there are 122 out of 23 out of 24 out of 20. So we can select many processes as possible. It depends again as your system configuration, so it may not be the same in each and every case. So transient, I will specify gravity in the negative direction minus 9.81 over here. So first of all, setting multi-phase model, so that in that multi-phase model I will select volume of fluid, I will say implicit body force, number of phases. Right now we are having 2. Later on we are going to make some modification over here when the phases we are defining, like we are not specified the material as of now, that is a fluid we are not specified. So we'll just go on to specify the material first, and then we'll come back to this again. So energy equation, I will just make it on, make it okay, then viscous K epsilon, you can select K epsilon, then you can select standard enhanced wall treatment thermal effect, you can say curvature correction. So make it okay, and let's go back to your material. Now here comes the material which we require. Say for example I'm using water liquid and water vapor, so I will just select the 2 working fluid over here and make it copy and close this window. So once this window is closed, you can observe water vapor and water liquid over here. Now next thing will be to go back to your model, the multi-phase model. Now in that case you may see water liquid and water vapor. So first of all I will specify the primary phase, say for example as steam, it will be your water vapor, make it apply. Now next one will be your water over here, we'll say water liquid, make it apply. Then phase interaction, you may have surface tension 0.0736. Now it depends on whatever fluid you are using. Different fluids may have different surface tension, accordingly the different value can also be used. Number of transfer mechanism, I will say 1. So water, it has to be specified as a steam, water converted into steam. So evaporation condensation, you can specify at what temperature the phase is likely to change. Say for example I specified it as 0.3. So make it okay, make it apply, and then close this window. Now you have water vapor, water liquid, you can select this 8978 381, and you can select this 387.6. if you want to select copper material, so you can make some variation, or directly you can go to the Fluent database, and through the Fluent database also you can change this value. So I made this change grade, now it will be copper which will be there instead of the aluminum which is there. Now next thing which we can be done is you can select the solid material, and from this also you can select the particular we can say either copper is there or some other material which you are having, so that can also be selected. If you know the properties, then it can be edited over here. If you don't know, directly go to the Fluent database and proceed. So this is the regarding to the material selection. Then zone condition, so operating condition which we are having, so that we have to specify. Say for example we have the 4000 as operating pressure, make it apply, then use the boundary condition we are done. Now where we are applying the boundary condition, that is also very important, so let's check it here. So say for example we are having the contact angle has to be selected, temperature, say for example if I apply 343 Kelvin and make it apply, close this window. Now you can check out the condenser also, you can check out the other parameters also. Only thing what you have to do is you have to change this to 20 and then close. So this is one heater, this is one wall over here, so make this as a apply. Every angle I am making as 20. I have not changed the boundary condition at other place, only I have changed the boundary condition at one place. So that also one thing that need to be remember. So this is again 20. So close this. So make it 20. So we are just applying the boundary conditions over here, so as to Now last boundary condition, again it is specifying this contact angle. At no place we have changed the temperature, only at heater we have changed. For remaining we have kept it as it is. So this is related to your boundary condition. Now it goes to your initialization. So make it initialize. So patch option will be available. So instead of this, select water, volume fraction is to be taken as 1 and patch with the vapor. So make it, sorry, patch with water, make it close. Then go to the calculation activities. So we are performing the iteration for longer duration, so you have to make it autosave so that even if power failure or other thing happen, it can be easily accessible. So first of all, animation, say for example we are observing water liquid. So you can specify that, specify new object, specify contours. So I will specify here as a phase, then volume fraction I will specify water. Now at what I will specify here, whatever walls I am having, that I am specifying over here. Just check it out at the condenser also. Check out color map option. I will specify float, make it close and make it, you can give the name also here, water liquid, make it save display. So here you can observe it from 0 to 1. So you make it, ensure that everything has been selected, save display, and you can close this. So this is water liquid. At what, how you want to see the, say I want to use the front view of object, so accordingly I set, make it okay. Okay, it says there is a unique name. I will say animation 1. I will have this front only, make it okay. Yeah, this is now work. So go to the calculations, then I will select adaptive. Why I select adaptive is because I don't want to be having a problem of current number, so that's why I'm specifying this adaptive. This one has to be specified as 0.0005, so as to reduce the computational time, as well as we don't want the problem of current number, and that's why this has been selected. So now next step will be to start calculation. So if I click on calculation, you will see some another window which is been opening. So this calculations has to be run for longer duration, so as to visualize the contour which we can get over here. So seems to be a quite long process because it will take time over here. So we'll just have to wait whether we can say any problem occurs with a given time step or not. So you can see at the same moment, you can see some liquid form is actually trying to move up. So some differentiation can also be observed after some particular time step at this particular point. So this has to be run for longer duration. I will just check it out once this process is run for somewhere around 500 and odd number of iterations. We'll check out whether the problem of current number, other things are happening. If the problem of current number appears, the best way to do this is the modify the mesh size according to whatever the dimensions you have prepared for your object, and just check it out with a different we can say size of the mesh, and according to the different time set we have to run the simulation. So this kind of thing can so the simulation is running. Approximately it has 23,300 iterations has completed. You can see the alternate liquid and vapor slug, which the process has just started to form alternate liquid and vapor slug. So this may take more time. As of now it is 23,000 iterations. We might have to go for higher value, and just let's check it out the time step. I guess it is somewhere around 700 time steps have been completed. This is a very fast process, so you might see over here as how many time steps has been completed. So might require more, because this is just where the first liquid vapor slug has reached only this point. We want this to complete move along this particular tube and come back again to the evaporator section. So we'll have to wait for some longer time in order to visualize the alternate liquid and vapor slug. So this is after performing around 3000 time step. So you can see how the fluid has been flowing in the tube. So we have the alternate liquid and vapor slugs which are moving towards the top, and at the same time you are observing somewhat light green color which shows the process which has condensation. The liquid vapor slug moving towards the condenser section, and we can say the vapor is transformed to a liquid. So heat transfer which is taking place in the form of sensible as well as latent heat. So the simulation, it has completed up to 5000 time step. We'll just see how visualization has been there. You can visualize this with the help of animation option available. So click on playback. This window will open. We'll just have, say for example, 100, and we'll just try to play this. So you can see how the liquid and vapor slug, they are moving towards the up. So this is after performing 5000 time step. If you want this the whole process, we might need to run this for longer duration of time step. So right now the time step is 5000, and it is somewhere around 1 lakh iteration we have performed. So we can again start the calculation over here. Before that you must save the work so that it can be used again. Say the saving of work is important, so that even if you close this window, it can be accessed later on without any problem with the data. So this is how I'm again starting with the calculation process. Ensure that it has been saved. Okay, now next thing will be again to calculate. So this is the simulation which has been performed up to 25,000 time step. We'll just check it out how the flow patterns are there with the help of playback option available. So just click on this one. I will specify 100. Just check it out how much how the fluid flow has been taking place. So as the process was interrupted, so that's why it's showing only 4980 time step. So that if you want to visualize everything, you can go to the post processor and visualize from 0 to 25,000. So right now it is for 5000 we are able to see. Just check it out how the flow pattern is. Okay, so you can see the liquid which is been coming down as it is going up. So we have the flow pattern which is alternate liquid and vapor slug which is moving up and down. So we are on the right way, so we can proceed with this simulation for some longer duration of a time. So right now this is 26th of September. The initial video, the simulation has started 2 days back, so it takes time as far as the longer time steps are being concerned. So this is a post processor in CFD simulation. We are now at 37,000 time step. So we are saving this simulation in the form of images as well as in the form of video file. So these are the contours of wall temperature. Right now it is 15,520. So we are preparing the simulation of the effect of wall temperature along the length of the tube. so that we can visualize with the help of the simulation. At the same time, we are saving the simulation in the form of image file as well as a video file.